Hello, here we're going to look at the Chapter 6 review. So, without graphing, it says to determine whether the function represents exponential growth or exponential decay. So let's talk about what this is talking about. Exponential functions are y equals a times b to the x. Now, the a value does not impact whether you're exponential growth or decay, right? Remember that growth looked like this, started off slow and then went really fast. Decay started off high and dropped really quick to where this one was growth. And we had that this one was decay. Now, in order to determine without graphing, it all comes down to the b value. The b value is what determines if you're growth or decay. You are exponential growth if your b value is greater than 1. Because anytime you're multiplying by a number bigger than 1, you will be growing. Decay occurred when b was in between 0 and 1. And the greater than 0 part was so that b couldn't be negative. We did need b to be a positive number. But if your b value is in between 0 and 1, then you are decaying. The examples that we saw of this from some of our more interesting studies during this was, one of the growth examples was a page of the Bible, and I think they said it was 0.001 centimeters. And then we were folding it onto itself, so it was doubling each time, right? And so remember that stack of paper was growing very tall. That was growth. One of the decays we looked at was that cup of coffee that was at somewhere around 196 degrees, and it was losing, I forget how much of it was, I'm just going to make it up here, but it was losing 12% of its heat over time, and then that is decay, because we're only keeping 88% of our previous value. So when we go through, it's all about the b value. We don't care what the a value is doing. 7 is greater than 1, so this is growth. On this one, we don't care about the a value. 2.5 is greater than 1. So it's growth. This one, remember, we don't care about the a value. 0.75 is in between 0 and 1. So this is decay. This here is a formula that helps us talk about investing. We looked at it just briefly, but I wanted to review it here because it's one of the more popular applications of exponential growth is retirement funds and things like that. This capital A and T is essentially standing for the amount of money, depending on, because it's a function, so A of T, the amount of money depending on the amount of time that it's been storing up. The little a represents your initial amount. So it's the amount that you're starting off with. So for example, up here in the coffee example, it was like 196 degrees or whatever it was. In that Bible example, the pages was very, very thin. Right? It was like 0.001 centimeters thick. So A is that initial amount. R is the rate, but that rate must be expressed as a decimal. And then time is T. And we can use this not only for investing money, but for regular old exponential growth and decay situations like this, where it says the population of Baynesville is 2,000. The population is supposed to grow by 10% each year for the next 5 years. How many people will live in Baynesville in 5 years? Well, we've got, the amount depending on the time. This equation in general would look like the initial amount of people they have, and then 1 plus the rate as a decimal to whatever the amount of time is. And on this particular case, they wanted to know the population after 5 years. So this is what we need to type into the equation to find out the value of. And all that is the population of 2000 growing by 10% 5 times. And when we type this in, we get a new population. So the amount of people after 5 years, if everything continues at that rate, is 3,221 people. And cities will use growth rates like this to estimate how many people they're going to have in their city in a certain amount of time, so that they know, do they need to build more roads or more bridges or widen highways, things like that. So, it says in 2009, there were 1,570 bears in a wildlife refuge. In 2010, the population had increased to approximately 1,884 bears. If this trend continues and the bear population is increasing exponentially, how many bears will there be in 2014? Okay, so here's how we have to do this one. We're going to have to go back and think about how we created exponential equations given 2 coordinate points. One key piece of information that we're going to want to talk about is this first point. We're going to want to set it up as year 0. We're going to count 2009 as year 0. And there was 1,570 bears. And then in the next year, so in 2010, so 1 year later, there were 1,884 bears. Okay, so we're going to use this to help us out. Now, whenever we're talking about year 0, this represents our A value. So right now, our equation is 1,570. We don't know what our B value is yet. What we're now going to do is use this second point to help us figure it out. I'm going to use this as my x-coordinate, and this is my y-coordinate, and I'm going to apply it to our equation. So we have 1,884 as the y-coordinate. We already knew that 1,570 was our initial amount, and we'd have b to the first. And b to the first power is just b. So the next step is to divide both sides by 1,570. And we'll get that b to the first power is equal to, and when I divide those, we get a b value of 1.2. Now, if that b would have been squared or cubed or anything like that, we would have just had to take the square root or cube root at this point, but we didn't have to on this one because it was already just b to the first power. So now what that tells us is that our equation is this. And they wanted to know how many bears will there be in year 2014. Well, 2014, if we subtract that year 1 was 2009, right, because we set that as year 1, we get that this is 5 years later. So we will now simply go in and replace the x with a 5. And when we type that in, we'll get an estimated population of, approximately 3,906 bears. So if this wildlife refuge only had so much space, or they were worried about there being too many bears, they might look at this data and make some decisions and be like, whoa, if this population keeps growing at the rate it's growing, we're going to have a lot more bears to deal with in 5 years. And then maybe they take different steps, such as, sharing some of the bears with another wildlife preserve, or who knows. But you use exponential growth and decay to make decisions like this. So this section here is talking to us about shifts. It says write a function for the indicated transformation. They gave us a function. They want it vertically stretched by a factor of 3. So I'm going to write out over here the way different things happened. Those were all the possible shifts. A values counted as a stretch or compression. H values moved you left or right, but the opposite of what you'd think because of the negative with the H. And then K values moved you up or down vertically. So in this first example, they've already given us a function. They now want it stretched by a factor of 3. So all I'll need to do is toss a 3 out in front of the function. Then they give us another function. They want it translated up 8 units. So up 8 units will be a separate plus 8. I don't want to put the plus 8 with the x up in the exponent because that would move us left or right. I want that 8 to be a k value at the end. This next section, I'll need to announce, depending on what year we're watching this, whether we covered it or not. In the school year 2019 to 2020, where we had the corona quarantine, we did not cover this. I'm going to go ahead and take a look at it here, though, for future years when this chapter maybe gets refined and maybe we do look at it. This formula that we just used is the most common exponential growth in decay. There is another one that's called continuously compounded. And when we watched the video about E, the video about E helped us see what continuously compounded meant. Continuously compounded means they'll do more than just wait until the end of the year to give you interest. And like on this model right here, this is assuming that they only look at the amount of interest they're going to be giving you like once a year. You can do other amounts such as monthly or weekly or daily. You know, there's lots of different ways to compound interest. Compounded continuously means just at every point in time, which might make you think that that amount's going to be infinite. But when we saw in that video about E, E's just a number. It's about 2.71. So the formula for this, if you ever see something that says compounded continuously, is this. P times E raised up to the RT. It's called PERT. People will say PERT for this as the formula, where P is the principal. You still have an interest rate and you have time. This basically makes interest acquire faster than this formula here. It's just another type of way that you can do interest. And certain things in nature will do this instead of using that previous formula. Because E shows up in a lot of naturally occurring phenomenon. And that's why when we are doing the inverse of E, it was Ln, right, with that invisible base E, and where Ln stood for the natural log, because E shows up in a lot of naturally occurring things in nature. So anyways, if we're going to do this, it's simple. We write out the principal. We have E. Now, the only thing that's interesting about this is you want your rate still as a decimal, but you don't put a 1 with it, because E essentially covers that 1 on this, and that's how it's majorly different than this formula. This formula needed the 1, which represented changing by nothing. When you're working with PERT, you don't need the 1 because the E takes care of that. And so you then just type this in. So 300 times E raised up to the 0.05 times 4 power would give us approximately $366.42. We could do it on this one too, to where we have y is equal to 650 times e raised up to 6.5% as a decimal times 20. And this one's going to be much larger because the amount of time that we're letting the interest gather is much larger. So this one grew quite a bit more than that previous example. You know, that one went from 300 to 366. This one went from 650 to thousands. And we had covered previously that time is one of the biggest components on making money if you're going to be investing. And that's why you have to work a long time to retire. So here it says, write each equation in logarithmic form. And so what this is our drop, log, and roll. So we'll have a base raised up to some power x is equal to y. We'll drop the log, we'll drop the base with a log, and then the x and y roll spots. And what it allowed us to do is get the exponent isolated. So for this one, we'd have log base 9. And then the 2 and the 81 would switch spots. Because remember, logarithms ask 9 to what power gives me 81? That's why the answer is 2. So for this one, we'd have log base 4 of 1024 is equal to 5. On this one, we'll drop the base, and we'll roll the 512 and the 3. Right? Because 8 to what power gives me 512? 8 to the third power. So evaluate each logarithm using change of base. Now the change of base formula was this. If we had log of some base of x, the change of base formula was doing log of x divided by log of the base, where we're now using the base of the invisible 10. Now, we also covered in the previous video that you can use the shortcut on your calculator, which is the alpha button, and then the window button, right, which if we have our calculator, we have alpha's right about here. Right, here's the second button. Here's alpha. So we'll need alpha, and then right there is your window button. And once we do that, when we hit alpha window, you'll then see that option 5 is log base. And that will give you the same answer. So for this one, you could do it from two ways. You could do log of 128, log of 2, using the log button down here, which is log base 10. Or if you use the alpha window, you could type it in and it would look just like this. Either way, whenever you go through and calculate this one, you would get the answer of 7. For this next one, when you do either one of those methods, so make sure whichever method you're using you understand, gives us 2.5. And then this last one would give us 1.5. So this section here is just to make sure that you can type in logarithms onto your calculator. So, in 2004, an earthquake of magnitude 7.0 shook a place in Indonesia. I don't know how to pronounce that name. Compare the intensity level of that earthquake to the intensity of each earthquake below. And so what this is reminding us is that the earthquake scale is logarithmic. So when you see the difference between earthquakes, like 5.1 to 6.1, you're like, oh, that one's just 1 unit apart. And then 6.1 to 7.1, that one's almost 1 unit apart. So it's like, does that mean that these are just 2 units apart? And we'll see that with this being logarithmic, that it's actually 10 times as worse per 1 unit. So that means that these earthquakes here, and we'll calculate it, we'll see that these are almost 10 times as bad. The 7.0 is almost 10 times as bad as the 6.1, which means 10 times 10 means that a 7.0 earthquake is going to be almost 100 times worse than a 5.1. And the way to calculate those using the formula was this. The earthquake formula was, it was log base 10 of the intensity was equal to the difference in the magnitudes. So for this one, we have log base 10 of, we're looking for the intensity. We have a 7.0 earthquake minus a 6.1 earthquake. So we have log base 10 of our answer I is equal to 0.9. And then this is where we need a loop and swoop to where we do 10 to the 0.9 power is equal to the difference in the intensities. And when we do that, we get the difference intensity on this one is 7.9. Right? So an earthquake of 7.0 is 7.9 times as more powerful as an earthquake of 6.1. Now let's do that same setup, but this time we're going to compare the 7.0 earthquake and a 5.1. So we'd have log base 10 is equal to a 1.9, and we'll do a loop and swoop. And this is the one where I said that this one's going to be closer to 100 times as bad. It ends up being 79 times as bad. Because that 0.1, makes a difference. So even the 0.1s in the scale make a big difference. If this would have just been a 5.0 earthquake, this answer would have been a straight up 100 times as bad. But that 0.1 takes a large amount off because of this being logarithmic, to where each number, like so the 6 and the 0.1, the 5 and the 0.1, the 7, each added value on that means the earthquake is, a lot more powerful because of the logarithmic scale.